Well, we have discussed regarding Faraday's law of electromagnetic induction, where we have mentioned that there is various methods of changing magnetic flux and thereby generating induced EMF. One of such important way how we can generate induced EMF is by changing area, which is the concept of motional EMF as popularly known. Now let us discuss and see to the figure that here in the figure we have the conducting loop. L is the width of the loop being present in uniform magnetic field B, and the magnetic field here is perpendicular to both the length of the conductor, the loop, and to the velocity. It is important to note that if any of the length side or the velocity which is parallel to the magnetic field are shown, then in that case there will not be any induced EMF, and any other angle subsequently made will develop certain theta concepts which will be discussed in our subsequent problem cases. But here we will consider that the width of the conducting loop and the velocity with which, or the speed with which it is pulled out, is both are perpendicular to the magnetic field which is externally provided, and v is the constant speed with which the loop is pulled out. X is the changing distance which is causing the magnetic flux to change, and therefore phi we mentioned, which is equal to capital B L into X, that is the flux enclosed by the loop. It is because phi being B dot A, here A being the Lx, L into X, which is the area of that part of the loop where magnetic flux is not zero. If the entire conducting loop is kept inside the external magnetic field or completely out of the magnetic field, then also you will not get any induced EMF. That's because there will not be any change in the flux within the loop enclosed. And here I will be our induced current in the loop. Capital R is the resistance of the loop, and F1, F2, F3 are respectively the magnetic forces acting on the current carrying conductor, which, as we have seen in previous discussions, that the magnetic force can be written as F is equal to I times L vector cross V vector, that is IL cross V. Just pulling out the conducting loop, then in that case there is a change in magnetic flux, and by Faraday's we have seen that the induced EMF must be equal to minus d phi by dt, that must be equal to minus d by dt of what is phi here. Phi I mentioned it, that is BLX, because phi is equal to B dot A and area being Lx, so phi equal to BLX, so therefore minus d by dt, in place of phi I have written BLX, so that equals to B, capital B and L being constant taken outside, what remains is B into L times within bracket minus dx by dt, and minus dx by dt I have taken here as the velocity with which the conducting loop is being pulled out. So therefore, as if the minus sign is against the induced EMF, such that it opposes the very cause as by Lenz's law. So therefore the induced EMF here is equal to BLV, which accommodates the sign as per the Lenz's law. Therefore, which is EMF, that is motional EMF, we say is equal to BLV. And once you get the expression for the motional EMF divided by the resistance of the loop, then you will get the current expressions, that is the induced current will be equal to I will be equal to BLV by R. If you see to the direction of the current is by Lenz's law is clockwise, that is this direction of current is such that it opposes the decrease in magnetic flux by setting of an additional magnetic field which is parallel to the external magnetic field present as shown in the diagram. Similarly, when you will be pushing into also, you will see that there is some magnetic flux will be subtracted out also. So magnetic force, now if you see the F1, F2, F3, which are the magnetic forces, out of these three, F2 and F3 they cancels out. That's because they are opposite and equal in magnitudes. If you apply the Lemming rules, then you can find that the direction of forces are equal and opposite to each other. That is, F2 and F3 cancels out, and what remains is F1 only. And F1 here is as shown in the diagrams. Direction of the force is as shown in the diagram, that is equal to, and magnitude equal to ILB sin 90. We are getting the magnetic force is equal to ILB. And once we have already got the expression for magnetic force, which is equal to ILB, we have got already the induced current expression, which is equal to BLV by R. So substituting that value for I, we get the magnetic force to be equal to BLV by R times LV, which gives finally B square L square V by R, which is the expression for magnetic force. We can find out the expression for mechanical work as required by the agent that must be doing somebody externally. That work must be equal to F into V. So therefore, substituting the expression for magnetic force, that is equal to B square L square V by R times V, we get the mechanical work expression to be equal to capital B square L square V square by R. And if you can check it, that our induced current will generate a heat, of course. So therefore the heat will be as per the Joule's heating effect, that is equal to I square R. So if you substitute the value for induced current, that is capital B L V by R, then your Joule's energy will become I square R, that will be equal to B square capital B square L square V square by R. So therefore, if you compare these two expressions, that is mechanical work and Joule's energy, they are equivalent. That means it is as in accordance with the conservation of energy, as if the work done, which is mechanically done by the external agent, goes as and appears in the form of equivalent electrical energy, which is providing the induced EMF or induced current, so as to say. And when the current is flowing, equivalent amount of Joule's energy is being created, that is thermal energy, which is also equal. So therefore, as if it is, this entire system is in a conservation of energy consequences. And the next figure, the agent is obviously experiencing always a opposition force, because if you three forces, three pictures we have shown here. In one of the case where conductor is at rest, then no field creation is there. That means there is no induced current or induced EMF will not be generated. So therefore, there is no additional magnetic field which will be created. And in the second figure, when you see that when the conductor is pulled out, as in our case of discussion, when we take away the conducting loop or pulled out, in that case the magnetic lines of force, as if it is opposing, it is bent, as shown in the picture, it is bent. That means as if it is opposing the motion and the agent is experiencing an opposition. Why? It is because additional magnetic field is being created, as we have seen in our case. And the same has been given in a dot and a cross manner in the ends of the conductors, if you carefully mark. And in the third figure, if you see, the conductor is pushed in that case the lines of force is as if pushed towards left, and thereby the magnetic flux is being ejected out. You can say it is ejected out. So therefore, the same magnetic field has been shown as given by a cross and dot at ends of the conductors. So therefore, this is an interesting phenomenon, how the consequence of Faraday's law can generate motional EMF. As because when you are changing the area, the phi being the magnetic flux, which is B dot A, is changing, because when area is changing, the magnetic flux is changing. Here the area is a function of time, you can say, as because in our discussions, when you are pulling out because area is changing with respect to time, so therefore there is a change in magnetic flux, and that is giving rise to concept of changing magnetic flux giving rise to motional EMF, or the induced EMF we call is as motional EMF. We will discuss more about the cases in our subsequent class. Thank you.